Good afternoon, everyone. My name is Singh Thapa. I am Assistant Professor in the Department of Mechanical Engineering at Kathmandu University in Nepal. Professor Choi, thank you very much for inviting me in this workshop and to present my research outcomes. Unfortunately, I could not be there physically, but I am very grateful that you provide me an opportunity to present it by online methods. If any one of you find my presentation uh, interesting, and if you want to communicate with me, please write to me. Even if I don't meet you physically in the workshop, we can talk about the future cooperation if that is interesting for you. So my topic is design and development of guide vane cascade for low speed normal Francis turbine. This is a part of my PhD work, and this is focused towards sediment erosion related issues. If you look at the hydropower development, more than 50% of hydropower developed worldwide falls in Asia, and moreover that, the future development, that is more than 60% of hydropower under development or planning phase, lies in Asia. So Asia is the center for hydropower development and will remain the center for hydropower development as well. But it comes with a challenge. It's not only the high undeveloped hydropower lies in Asia, the highest sediments also comes from Asian rivers. Almost 50% of sediment deposition worldwide is contributed from Asian rivers, and it has a problem in the performance of the hydro turbines. So we can say that the future hydropower development will occur in the region with sediment laden flows, and that is the center for my research. How the turbine performs in sediment laden flows, because this is the future of. I'm concentrated towards the Francis turbine. That's a field of my research. This is the simplified drawing of the Francis turbine. The water enters the spiral casing from the inlet, from the penstock. Water comes to the inlet, and there is the guide vane that regulates the flow and also directs flow to the runner. So from the guide vane, the flow comes to the runner, and the spinning or the energy conversion happens in runner, and the water coming from the runner goes to the draft tube and to the exit or tail race. So this is how basically Francis turbine works. This was developed 150 years ago, so it is a very mature technology, and 60% of the global hydropower in the world uses Francis turbines. So it has a very wide operating range and flexibility that makes it quite diverse. Due to a long experience, the companies like Voyage, they use the standard Francis turbine design methods. So they don't design turbine for all the projects. So they have a template. They use some standard principles to design the smaller turbines up to 25 or up to 50 megawatts. The turbines are completely designed from scratch only for a very big projects. So that makes the standard Francis turbine into some kind of trouble when it comes to the erosion related things, and that is what. So if you look towards the design philosophy of the Francis turbine, in order to have a very high efficiency, Francis turbine claims to have more than 96% of hydraulic efficiency. So to obtain this efficiency, the water in the spiral casing, which is moving around 10 to 15 meters per second, accelerates quite rapidly, and before it exits the guide vane, 50% of the total head is converted into the velocity head. So that brings the very peak velocity at the guide vane peripheral, and from the guide vane, when the water enters inside the runner, that is the relative velocity starts, and the velocity field drops abruptly at the inlet of the runner, and slowly it accelerates, and again at the outlet the velocity is quite high. So you can see that at the guide vane and at the runner outlet there are two velocity peaks. And when it comes to the sediment erosion, it is related with the cube of velocity, so exponentially 4 times of the velocity. So if the velocity is increasing by twice, erosion will be increasing by 8-fold, and that brings the standard Francis turbine very efficient in clean water a big problem in the water with the sediments. This is the Francis turbine. In fact, the biggest Francis turbine installed in Nepal, 48 megawatts. And at the outlet, you can see almost 30% of the runner blades is washed off due to the sediments. Several methods has been tried. You can see some remains of HBOF coating, which are very hard coating. Even that doesn't work well, and this is due to the high velocity peaks in the standard Francis turbine. This is the biggest Francis turbine installed in Nepal, installed in India actually. It's a 250 megawatt Francis turbine, and due to the very high velocity peaks around guide vanes, you can see how the guide vanes is eroded between the cover plates and the walls. So we can see there exists a very big gap between the plates and wall, and this gap and this erosion problem is my research problem. So I investigated this problem in depth and tried to find out why does it happen at first place, how does it affect the downstream flow, and what can be done to minimize this. So this is there has been some measurements in the power plants. So in the same power plant, the biggest power plant in Nepal, the gap between the guide vane and the cover plate has been done. So this is the reference line. So the initial design is the clearance gap should be 0.3 millimeters, but due to erosion by the sediments, this gap is increasing, and this has been measured up to 6 millimeters, the total gap. So 3 millimeters on each side is the average gap, and this is due to the erosion of the guide vanes. This is the trailing edge, and that is my focus. Why does this increase so rapidly, and what does it do to the other components? So I set up with the hypothesis, what we call is the dry clearance gap. That is, the walls or the cover plates and guide vanes have a small clearance gap around 0.1 to 0.3 that is needed for guide vane to move. But the flow with the sediments, they slowly erode the material and causes the increase in the gap of the guide vane. And due to the pressure difference of the guide vanes towards the pressure side and suction side, the leakage flow starts from the increased clearance gap, and this leakage flow disturbs the main flow at the runner, and this disturbances causes reduction in efficiency of the whole turbine and also increase in erosion of the runner and other components. So this is my hypothesis. I started with this hypothesis and I wanted to test this. So this is my research objective. I want to focus why is the clearance gap happening and what does this affect towards the runner. Does the clearance gap contribute to more erosion in the runner? So that's something I want to investigate. So I choose the experimental method. I did a lot of CFDs to formulate my research hypothesis, and also a lot of CFDs to develop my experimental setup, but the final results were coming from my experimental setup. So I started with my research from PIV techniques. So I need to develop a cascade that would produce the same velocity conditions as that in the real prototype, and also gives me the flexibility to use the PIV. So the whole flow channel was developed in a plexiglass, and even the parts of guide vane that I was investigating was also developed from plexiglass, and everything was compact and tested in the test setup, which looks close to like this. So in order to design the test setup, I started with a reference design. So this is a Jimruk Power Hydroelectric Center, JHC, in Nepal, that also reports a very severe erosion in the guide vanes and in the runner. So I selected 3 guide vanes towards the end of the spiral casing and then isolate it. So these are the 3 guide vanes. So I also ignored the runner, but I wanted to produce the same velocity at the section where the runner would be present in case of the real turbine. So this will cover 30% of the flow field inside the runner. So from this layout, the main layout was developed, and this layout was determined by several stages of optimization, and the goal was to create the same velocity field that is occurring in the real Francis turbine. So in a Francis turbine, the flow coming from the spiral casing to the stay vanes and from the guide vanes and to the runner. So if you look closely towards guide vane and runner, the main velocity, that is CRin, that is the total velocity, is decomposed into the tangential component and the radial component, and the difference between these two is the relative velocity, and this is forms the velocity triangle. So my aim was to develop the cascade that will give the similar velocity triangle at the runner inlet at this section. So several optimizations were done on the walls so that the flow is directed towards the runner inlet, producing the similar velocity triangles. It was not possible to come exactly close. The walls did have some effects, but we tried to come as close as possible, and all the optimization were done by CFD. So I have some references at the end of my presentation where we have discussed quite intensively how the optimization were done. So these are the reference values for the real the main prototype turbine. So our target was to have the similar velocity components in the cascade as well. So the cascade was developed as a test setup, and this was installed at the water power laboratory in Norwegian University of Science and Technology, which is also called as NTNU in Norway. So in order to have the test to produce the test setup to produce the high velocity, the water was pressurized up to 8 bars. Heavily pressurized water, when entered to the guide vanes or inside the cascade around the runner inlet, the very high velocity was produced, both in tangential and the radial direction. So the test was not done at the best efficiency flow or the design flow due to the limitations. The velocity field was developed around 80% of the design condition, but still we were close to 35 meters per second, and as far as we know, this velocity is the highest velocity developed for the experimental investigation in a Francis turbine in laboratory conditions. And we tried not to let the flow cavitate by itself, so we maintained the minimum pressure inside the test setup above the atmospheric pressure. So to maintain this pressure above atmospheric pressure, so we need to have a very high pressure in the pressure tank. So we did both velocity measurements and the pressure measurements, and the guide vane we choose for our case was symmetric NACA profiles. Particularly for my case, I choose NACA 0012, and then the pressure measurements were done at the mid span to see how the pressure difference occurs between the pressure and the suction side in the Francis turbines operating conditions. And we also measured the pressure difference at the walls with and without clearance gap. So we wanted to see how the clearance gap affects the pressure difference. The velocity measurements, and we used PIV methods. So this is the parts of my test setup with and these blue dots representing the PIV resolution. So it's around 4.7 millimeters. It's not a very dense PIV, but still we got some very reliable results. So the span of this is the in the radial view. So on the axial view, if you consider a runner, so we started from the walls of the guide vanes, we choose NACA profile, and we did test without any clearance gap, so without no clearance gap, and then with 0.5, 1.5, 2 and 3 millimeter clearance gap. And the measurements were started from the walls, and then we went up to the mid span of the guide vane, and we assumed the flow is symmetric on the guide vane axis. So this was our measurement location. Of course, we did not have the runner blade, but if the runner were present, it would look like this. So these are some images from the PIV. You can see that there has been some reflections at the leading edge, and also some reflections on this location due to the plexiglass. We did the uncertainty and bad vector analysis. So we can see that bad vectors were present due to the reflections, but the total bad vectors were kept around 11%. It's not a very good number, but we were not able to reduce bad vector below this because of our test rig limitations. We also did the conversion test, so we wanted to identify minimum number of images needed for good correlation, because we had a very high bad vectors. So we found that 60 was the limit from where both velocities and standard deviations at runner inlet were converging. So we decided to go for 100. So all the measurements were done at least with 100 image pairs. We also did some analysis to test if the flow are repeatable, and we found that the flows from the different days of measurements were repeating. It was not a high error towards the walls. We can understand that due to the boundary layer effects, but toward the center of the flow was quite repeating. So let's see some questions. So this is the pressure measurements. So we can see that there exists a very high pressure difference between the guide vane pressure side. So this is the pressure side and this is the suction side. So at around 75% of the guide vane cord from the leading edge. So this is the leading edge and this is the trailing edge, and this is around 75% of the guide vane cord. There was the highest difference between the pressure and suction side, and we found it was approximately 20% of the total nominal head for the whole power plant. So this was a very high pressure difference. And this is the velocity field. So without any clearance, the velocity field is very smooth, and then we can see high velocities towards the suction side and low velocity towards the pressure side. And these are the contours from the PIV measurements with and without clearance gap. So without any clearance gap, or the position where the flow is towards the mid span, we can see a very smooth patterns of the flow. So this is what we wanted in a real turbine, and this is what happening in the guide vane mid span. But due to the clearance gap, we can see the flow is passing from the pressure side to the suction side. So this is the flow field along the clearance gap, and we saw that the high pressure difference was around 75%. So due to the high pressure difference along the guide vane surfaces, the flow was driven from the pressure side and suction side, and this leakage flow is mixing with the main flow, and we can see the sudden drop in the velocity. So this could originate some kind of vortex field at this point. So we have done intensive analysis of how the pressure distribution affects the flow field. So we can see that this is the pressure field without any clearance gap. So when the clearance gap is coming up from 0.5, 1.5, 2 and 3, the pressure distribution pattern along the clearance gap is changing. Of course, that is due to the leakage flow that makes the pressure difference in the clearance gap change. But what is most interesting to us is the pressure difference between the pressure and suction side. So this is the differential pressure between the pressure and suction side. We can see that the highest differential pressure is around 75 to 80%. So there are some strange phenomenon, and I will not discuss it over here, but what we can see that there exists negative pressure difference with the high clearance gap, and this negative pressure difference actually causes the guide vane, because there is a high pressure difference here. So this is the high pressure difference, positive pressure difference from the pressure side to suction side, and this is the negative pressure difference for the high clearance gap. So this pressure difference causes the torque on the guide vane shaft to increase, and what we found was it increased quite a lot. And then due to the differential pressure and also the additional negative pressure due to the clearance gap, the total guide vane torque was increasing quite high, up to 28%. We did many other studies as well, and I don't discuss it much, but what I would like to say that if we see the leakage flow from the guide vane clearance gap, from this gap, it was found to be highest for 2 millimeter clearance gap, and that was approximately more than 1% of the main flow. And this leakage flow was mixing with the main flow and disturbing the flow conditions at runner inlet. So we did the flow conditions. I also studied the flow conditions at runner inlet on both Cu, Cm, and the relative velocity W and beta distributions. All the velocity components, Cu, Cm, W and beta, all were disturbed. All the velocity field were disturbed due to the leakage flow. Strangely, we found reduction in Cu, and reduction in Cu is actually reduction in efficiency. We found increase in Cm, so that is to compensate increase in Cu. So that is actually the accelerating flow. And most remarkably, we found the relative velocity that is going towards the runner, increasing almost 3 times, very locally, but 3 times. So this increase is actually related to the sediment erosion at the runner inlet. If the relative velocity increasing by 3 times, the erosion might increase by 27 times or 29 times. So even the beta distributions, the angle, that is what is called at the runner inlet angle, is also deflating. It also have some consequences. I don't discuss. And I made a study on the vorticity. This was what observed from the test rig. This is the vortex due to the mixing of the leakage flow from the pressure side to the suction side, and the leakage flow was mixing with the main flow, and this vortex was generated. And we did study this vortex field. I will not go into details about what were the results. It's on my but definitely I would like to show you that if this is the guide vanes in my this is the guide vane in my test rig, this is the wall, this is the clearance gap, and this is the vortex. So that is coming from due to mixing of the fluid from the pressure side to the suction side. But if I place a runner here, the runner would look like this, and you can see the vortex is hitting towards the shroud at this position. And if we observe at this location in the real project, we can see this kind of phenomenon. Then I can relate these two happenings and say that they do have a very big correlation, and this erosion could be due to the erosion in guide vanes, and we have seen for the same power plants the guide vanes were very heavily eroded. So finally, if I explain the observations, all these 3 power plants in the different part of the world, they have symmetric NACA profile, and all the guide vanes are eroding in the trailing edge, and all the runners are having erosion in the inlet towards the shroud or hub. And if I explain this, of course it is due to the symmetric NACA profile. All the NACA profile are symmetric in these projects, and that causes high pressure difference towards the trailing edge, and this high pressure trailing towards the trailing edge and is causing the secondary flows, and that increases the clearance gap, and increase in clearance gap causes higher relative velocity and lower tangential velocity, and high relative velocity means high erosion, and lower tangential velocity is lower efficiency. So they do correlate, and that was my finding. So the future work, one more PhD has started, and he is looking towards the alternative design of guide vanes. I will not explain it much. I am running out of time, I know that. So we have seen that compared to NACA 0012 profile, NACA 4412 and NACA 2412 are giving better results. So we can see the vortex field is reduced in 4412. So and he is now, the next PhD is upgrading towards the 3 guide vane cascade, and he has done a lot of CFD works, and we are installing this 3 guide vane cascade in the water power lab at Kathmandu University now. And then what we expect, the effect of the walls will be minimized, and we will get better results, and also we can test at the different guide vane opening angles. So let me conclude my presentation for today. So my first conclusion is Francis turbine designed with standard methods are not suitable for sediment laden projects. It's due to the inherent velocity peaks around guide vanes and at the runner outlet that makes the very good Francis turbines very bad with sediments. And we found that the design of guide vanes play a very important role, particularly the profile. The symmetric NACA profile was found not to be a suitable one for sediment laden projects because of the high pressure difference towards the trailing edge, and this induced erosion in turbine components as well. What was found, another finding was the clearance gap that should never reach the critical size. In our case it was 2 millimeters that produces the highest effect for the velocity profiles. So it might be different for different power plants, but it should be very carefully investigated, and it should be aimed at this critical size of the clearance gap should be avoided. The choice of guide vane axis should be carefully done for sediment laden process, because due to the leakage flow, the total guide vane torque might increase quite significantly. For our case, it was estimated that 28% rise in the guide vane torque. If only 25% of safety factor was chosen, then this would be failed in case of the guide vane or in case of the sediment laden projects. We have a very big market in Asia for the hydropower development, and that comes with the sediment challenges. So more studies are needed so that the standard design of the Francis turbine can be modified or updated or optimized so that they are feasible and they can perform well for the future market in Asia. So thank you very much for your kind attention. Unfortunately, I cannot take any questions because I'm in distant mode, but these are the references for my presentations. These were the publications that I managed to come up with my research work from these studies. If anybody of you have any suggestions, any questions, any future discussions, please do write to me in my email. Once again, thank you very much for listening to me. I could not be there. Thank you very much, Professor Choi, for all the supports and cooperations you have had for me. Thank you very much, and I end my presentation here. Bye bye.